Welcome to a foundational journey into the world of artificial neural networks. Today, we'll demystify the core components that make these powerful systems work: perceptrons, multi-layer perceptrons, and the crucial role of activation functions. At its heart, a neural network is inspired by the human brain, composed of interconnected neurons. Our simplest artificial neuron is called a perceptron, a groundbreaking concept from the late 1950s that laid the groundwork for modern AI. Imagine a perceptron as a tiny decision maker. It receives multiple inputs, each assigned a numerical weight representing its importance. These inputs are multiplied by their respective weights, then summed together along with an additional term called the bias, which helps shift the activation function. This weighted sum then passes through a simple threshold function. If the sum exceeds a certain value, the perceptron fires or outputs a 1, otherwise, it outputs a 0. This allows it to classify data into one of two categories, effectively drawing a straight line to separate them. While powerful for simple problems like logical and OR gates, the single-layer perceptron had a significant limitation: it couldn't solve nonlinear problems, most famously the XOR problem. This discovery halted AI research for a time, leading to what was known as the AI winter. The breakthrough came with the introduction of multi-layer perceptrons, or MLPs. Unlike a single perceptron, MLPs feature one or more hidden layers between the input and output layers, allowing them to learn much more complex, nonlinear relationships. An MLP's architecture starts with an input layer receiving raw data, like pixels in an image. These inputs feed into the first hidden layer, which processes the information, then passes it to subsequent hidden layers, until finally reaching the output layer, which provides the network's prediction. Each connection between layers has its own weight and bias. Now, if every neuron simply applied a linear transformation or a step function, stacking layers wouldn't add much power beyond a single layer. This is where activation functions become indispensable. They introduce nonlinearity, enabling the network to learn intricate patterns. Two early and popular activation functions are sigmoid and tan. The sigmoid function squashes any input value into an output between 0 and 1, making it ideal for probabilities or binary classification. Tan, or hyperbolic tangent, is similar but maps outputs between -1 and 1, often performing better than sigmoid in hidden layers due to its zero-centered output. However, sigmoid and tan suffer from the vanishing gradient problem, where gradients become very small during backpropagation, slowing down learning. This led to the rise of rectified linear units, or ReLU, which simply outputs the input if it's positive, and 0 otherwise. ReLU's simplicity and computational efficiency have made it a cornerstone of modern deep learning. Ultimately, activation functions are the secret sauce that allows neural networks to approximate any continuous function. By introducing nonlinearity, they enable MLPs to move beyond simple linear boundaries, learning hierarchical representations and extracting increasingly abstract features from data, from identifying edges to recognizing entire objects. From the humble perceptron to the sophisticated multi-layer perceptron, these building blocks form the foundation of today's AI revolution. Understanding how inputs, weights, biases, and especially activation functions collaborate is key to grasping the power and potential of deep learning.